Yeah, hello everyone. My name is Ibrahim, and I'll be the one presenting the Introduction to Machine Learning tutorial. And feel free to stop me when you have a question, so you can just post it on Slack and I'll attend to it. I'll just stop in between the tutorial to attend to questions. So without further ado, I'm just going to start. My name is Ibrahim, and I'm a PhD student in Boise State University. I just finished my first year, as HP has said. And then the learning objectives of this tutorial is to understand the goals and main concepts of machine learning algorithms, to prepare a SnowEx data set for machine learning, to understand the fundamental types of and then techniques in machine learning, and to implement machine learning with a SnowEx data sets. I start by defining what is machine learning. There are many definitions to machine learning, but I prefer to go by a simple one, which means building algorithms or computer models using data. And the goals of every machine learning is to use the trained computer models to make decisions. And then there's a more general definitions by Arthur Summer since 1959, who says machine learning is the field of study that gives computer the ability to learn without being explicitly programmed. So in simple language, when we talk about machine learning, we really mean building models with data, and then the goal of the trained models is to make decisions. And over the years, machine learning have been used to achieve it has achieved great successes in a wide variety of fields, and we have examples including disease diagnostics, image recognition, self-driving cars, spam detectors, and handwritten disease recognitions. So in this tutorial, we'll train a model using a SnowEx dataset. So to further understand what machine learning is, I'm going to have to give a simple analogy using this binary example. Let's suppose we want to build a computer model, or let's to make it simpler, let's assume we want to write a function that returns 1 if a number input is a prime number or 0 otherwise. So what I just said now can be represented mathematically using y equals to a function of x, where x is the number that I entered, and then y is the outcome that I want to predict, and f is the function that gets it done. So for example, if I pass in 2 as my x, then my function is going to predict y as prime. And if I pass in something like 9, my function is going to predict y as not a prime. So contrary to classical programming, let's assume we want to carry out this task in classical programming. Since we know what we want to do, we just write the rules. That is, we try to write a function that gives every prime number a prediction of 1 and gives every non-prime number a prediction of 0. So this is how we would solve the problem if it were to be classical programming. However, in machine learning, the way we are going to solve the problem is going to be different. What we do is we have the predicted outcomes. We have the outcomes, which is the ground truth. Then we show it some data sets, and then the machine learning algorithm try to learn the rules such that when you feed in some data sets, it gives you the prediction of the unknown outcome. So contrary to the classical programming, in machine learning, we learn the rules, we don't program the rules. But in classical programming, we program the rules to get the answer. In machine learning, we train our model to learn the rules. So machine learning is useful when the function cannot be programmed. Like the function I mentioned now is a very simple function that could be programmed, but in reality, we almost don't know the function that maps the input to the output. So machine learning comes in when we do not know how to program the function, or we do not know the relationship between the features and the outcome. So now, I mentioned here that we show our machine learning, we train our machine learning algorithm using some data sets. So it is a good time to introduce what a data set is. So in this tutorial, we're going to work with a data set from the 2017 SnowEx campaign. And then the data set has some features and outcome. In machine learning terms, features means the variables that we want to use to predict something. And it goes by many names. It could be called predictors. It could be called independent variables. They are used interchangeably. It's called features. And what we want to predict is always called the outcome. And also it goes by many names. It could be called the dependent variable. It could be called the label. It could be called the target, and anyone goes. So the outcome variable is what we want to predict, and the features is what we want to predict, what we want to use in predicting the outcome variable. So the goal is to use the data set we have to learn the computer model F such that you have a snow depth as a function of the independent variables or the predictors, such that once you have learned the function or the machine learning algorithm, it can be used to predict the snow depth given the features. So in other words, machine learning is really concerned about how to form this F, which is just the machine learning algorithms or the models that predicts our snow depth given the features. So,
and Ibrahim, just sorry to interrupt, just to give people a little bit of context there. The phase coherence, amplitude, and incidence angle is from UAV SAR, from the INSAR observations over Grand Mesa, and then the outcome, sort of the calibration validation piece, is the snow depths from the LiDAR. Great job, Ibrahim. I just want to give that context. Go ahead.
Yeah, thank you. So now we're gonna load the data set into our Jupyter Lab, and then I'm gonna use all these packages. So most of these packages have been used in the past. NumPy is used in just manipulating arrays. The pandas is going to use for manipulating data frames. The Seaborn is going to be used for visualizations, and then Matplotlib is also going to be used for visualization. And here, the scikit-learn here is going to be used for data processing and some error matrix computation. So this is the code that brings in my data into the Jupyter Lab. My data is a CSV data called the snow depth data. And then this .info gives me some information about my data sets. And then this .head just gives me the first 5 observations in my data sets. So looking at this, we have a data set of 3,000 entries. And then we have the column, which is which we have the amplitude, the coherence, the phase, the incidence angle, and the snow depth. These are the variables we have here. And then each of these variables does not have any missing observation. That is what this means. It says 3,000 null, and then everything is a float. So float means it's a decimal point, like the values are decimal. And then this dataset.head gives me this information. This is just the first 5 observations in my dataset. And then this is useful because we have a sense as to what the observations look like. So moving ahead, we move to train and test sets. We've mentioned that algorithms learn from data, but then for the algorithms to learn from data sets, we have to show it some data sets. So, and then the data set that the algorithm used in learning is called the training set. So in practice, when you have a data set, you divide it into training and testing sets. So you train your model on the training set, and then you predict or you evaluate its performance on the test set. The test set is really just a kind of mirror of reality. You never use it in training because in reality, you do not have the data you want to use the trained model to predict. So we use the test set to mirror the reality. So the test set is going to be used to evaluate the performance of our model. It is never going to be included in the model at all. So what we do in practice is we divide our data set into training and test. We train the algorithm on the training set, and then we evaluate its performance on the test set. So we now move ahead to divide our data set into training and test sets. So this code divides my data into training and test sets. So I'm randomly sampling 80% of my data sets as the training set, and then 20% as the test set. And then it is not compulsory that I use 80% as training sets. You could use 70, you could use even 90 at times, depending on the size of your data set. So, but one common rule of thumb is to use the 80% of the entire data set as a training set. And then this random states ensures that I get the same observation every time. So this is just like for a reproducible result. So if I didn't set a random state, every time I resample my data set, then it's going to give me a separate sample. So I'm just setting this random states to 0. And this could be any integer. I'm just using 0 here. And then I drop out the training set from the entire data set. And then the remaining one is going to be my test set. And that is what this code here is doing. So after dividing my data into training and test sets, the next thing we have to do is to inspect the data set. At this point, it is important to note that we do not touch our test set again. Every other thing we want to do from now on is going to be done on the training sets. So the first thing we want to do is to visualize our data sets. Before modeling, it is always a good idea to visualize our data sets, and we have many reasons for that. With visualizations, you can get or you gain insights into the relationship pattern, and you look at how the shape of each of the variables, how they are distributed, if they have outliers or not, and many more. So here we have a scatter plot and a matrix of scatter plots that contains the scatter plot of all the variables in the model. Each panel, excluding the main diagonal of the scatter plot matrix, is a scatter plot for a pair of variables whose identities are given by the corresponding row and column labels. So as an example, this is a scatter plot of snow depth and incidence angle. This is a scatter plot of amplitude and the incidence angle, and it goes on like that. On this diagonal, we have the distribution, the shape of the distribution. So this is like an histogram, but here we are not using the histogram per se, we are just using the distribution, and that is what this KDE means. KDE is a way of estimating the distribution, or the density rather, estimating the density of a particular variable. So if you had plotted the histogram of snow depth as an example, then it would have looked like this. It would look like something like this. And then inspecting this would kind of have a way to look at how these variables are related. As an example, we do not see any linear relationship here. Most of them are nonlinear. For example, there's no linear relationship between snow depth and incidence angle, no linear relationship between snow depth and phase. All of them, there is no linear relationship between the outcome we want to predict and the independent variables we want to use in predicting the outcome. So this might give us a sense that a linear model might not be the best to use in this case, because the relationship between what we want to predict and what we want to use to predict, which are the features, are really not linear. So after we describe our dataset using the visual tools, we would want to describe them using some summary statistics. And here, the pandas gives us some summary statistics. We have the count, the mean, the standard deviation, then the 5 number summaries. So here we have the count, and the count is the size of the training set. The mean is the average of each of the variable. The standard deviation is the spread across around the mean for each of the variable. Then this 25%, what it means is the 25th percentile, which is just saying 25% of the values fall below the particular number. 50% is called the median, and which means 50% of the data value falls below that number, and then 50% falls above the number. 75% is the same thing as the 75th percentile, which means 75% of the values fall below this number, and then we have the maximum value. So looking at this as an example, taking the snow depth, we have 2,400 observations in the training set. We have a mean of 1.17. We have a standard deviation of 0.629. And then we have the minimum snow depth is 0.05. Then 25th percentile is 0.66, which means 25% of the values of the snow depth fall below 0.66. Then we have a median of 0.96, which means 50% of all the snow depth measurement fall below 0.96, and 50% falls above 0.96. Then we have the 75th percentile, which means 75% of the snow depth measurements fall below 1.65. And then we have the maximum, which means the maximum snow depth we have in this data set is 2.55. So one reason why we always want to look at the descriptive statistics is to have an idea of how different the scales of our training set is. So as an example, if you look at the minimum value of the amplitude, it is 0.07. We look at the minimum value of the phase, it is -8. We look at the minimum value of the snow depth, this is 0.66. There is heterogeneity in the scales, that is, the scales are not on the same range. And this could be the source of modeling difficulties for us. With the exceptions of few machine learning models would always encounter difficulty when we train it with data that are on different scales. And to solve this problem, there are two major ways to do that. We have the normalization and we have the standardization. For this tutorial, I'm going to stick with the normalization, which just consists of transforming all the variables to a unit interval 0.1. That is, when you transform your variables, all of the variables are going to take values in the range 0.1, with the minimum value of each of the variables being 0, and then the maximum value being 1. So, and then this is achieved using this formula. With normalization, if xj is one of the variable, so let's take as an example, phase here. So if I want to normalize phase here, what I'm going to do is for every observation of phase, I'm going to have the normalized version. And then for me to get the normalized version of every values for the phase, then I take the original value minus the minimum value for phase, which in this case, it is -9.24. Then I divide it by the maximum value of phase, which in this case is -7.69, and I divide it by the difference between the maximum and the minimum. Then with that, I'm going to get the normalized version. And the essence of this normalized version is to put all the variables into the same scale. And with that, our machine learning could train faster and then improve generalizations. So I'm going to achieve that in Python using the min-max scalar. And the min-max scalar is I've imported it from the scikit-learn up here. So I've imported it from the scikit-learn.preprocessing. I imported the min-max scalar. So that is what I'm going to use. So at this point, it is also important to note that I'm going to transform my training sets, but then I'm going to use the mean and the minimum value and the maximum value that I got from my training set in transforming my test set, because like I've said, we do not touch the test set at all. So fit transform gets the mean and the maximum for all the variables and then transforms our training set, but transform itself uses the parameters we've gotten from the fit transform to transform the test set, which means I don't have to get the mean and the minimum value of each variables in the test set and the maximum values of each variables in the test set. I just use the minimum and maximum values of the variables that I've learned from my training sets. So the final step is to separate the feature and the labels. And here, it depends on the Python package you're using. I'm doing this because I'm using Tensorflow, and Tensorflow requires that you separate the predictors and the outcome. So that is why I'm doing this. Then I'm using my scale train because I've transformed my variable here. And then I'm using my scale test here because I've also transformed it right here. And then this -1 implies that my training set, which is my train X, I have train X, train Y, which means this is my train X. Then what comes after the comma is my train Y. And then this -1 means I'm picking all the variables except the last one. And then here, this means I'm just picking the last variable here. So if you notice, before the comma, there is a full colon, then after the comma, there is also a full colon before the -1. But right here, after the comma, there is no full colon before the negative one, which means the last variable is my y variable or is my outcome that I want to predict. And that has been done. I did it like that because if you notice our data sets, the last variable here is the snow depth that I want to predict. So it's very important to keep track of the position where you have your predictor, you have your predictors and then your outcome. So in most cases, you want to put your predictor as the last variable or as the first variable because it makes modeling easy. And then after doing that, we have our train X, we have our train Y, we have a test X, we have a test Y, where the train X are the predictors from the training set, and the train Y are the outcome from the training set. The test X are the predictors from the test set, and the test Y are the predictors from the test set, are the outcome from the test sets. So now I've mentioned that machine learning is really just about estimating the function, estimating the computer models or the algorithm that we often represent with F. So now it is important to know why we have to estimate or why we have to learn this F. So we estimate F or we estimate the machine learning algorithm for two reasons. The first one is for prediction purpose and the second one is for inference purpose. So by prediction, what we mean is we are just concerned about predicting the future values or predicting an unknown outcome. So in that case, we would always know the X variables or we always know the features, but then we do not know the outcome. So we try to learn the representation or we try to learn an algorithm that is going to predict our outcome given the features. The other reason why we would want to do machine learning is for inference sake. And in this case, we are not only concerned about prediction, but we want to look at how changing the X variables are going to affect the Y variable. So one of such things is you want to look at the nature of the relationship between the X and Y, and you want to see if whether increasing X increases Y also or decreases Y. Or you want to see if there is a significant association between your predictor variables and then the outcome variables. So if that is the goal of your machine learning, then you are doing inference. Or if you are just all about predicting an unknown outcome, then that is called prediction. So now that we know why we want to estimate F, then it's a good time to introduce how to estimate F. So for us to estimate F, is very important to know about machine learning algorithms. Machine learning algorithms can be categorized based on different criteria, but in this tutorial, our categorization is going to be based on the amount of supervision needed during the training process. So based on the amount of supervision you need, there are 4 categories of machine learning. We have the supervised learning, we have the unsupervised learning, we have the semi-supervised learning, and then we have the reinforcement learning. So in this tutorial, we will limit our definition to the first 2 because our goal in this tutorial is more related to these first 2. The first one is the supervised learning. And then when you have a Y to predict, or when you have a variable you want to predict, you are doing a supervised learning. That is, you have a Y that is supervised, you have an outcome that is supervising the model that you are training. So what that means is there is a value that you want to estimate. And that is every observation of the feature has a corresponding outcome. So the outcome supervises the features. So an example of supervised learning task is predicting snow depth based on some influencing features, just as the ones we've mentioned above. Then on the other hand, we have an unsupervised learning. And in this case, we assume you don't have a snow depth, but then you want to try to look at the relationship between the observations in your data set, or you look at the relationship between the variables. So some of the algorithms you commonly use in that case is clustering. You might want to cluster all the observations based on the features you have, or you want to try to reduce the dimensions. Maybe you have too many variables. You want to try to reduce the dimension. In that case, you're not predicting, you're just reducing the dimension. So in that case, you don't have any outcome variable to supervise your features. And some algorithms used in that case we have clustering, we have PCA, and the likes. So now, since we are predicting snow depth in this case, we are doing a supervised learning task in this tutorial. So it is worth noting that each variable can be categorical or continuous. So for now, we should focus on the nature of the outcome variable. In supervised learning, if the outcome variable, that is what we want to predict, is categorical, then it is called a classification task. Or if it is continuous, it is called a regression task. So categorical simply means it is the variable consists of distinct categories, such as you may have a picture that is snow off or snow on, something like that. Since it is divided into categories, then in that case, what we are doing is what is classification, because our y variable or our outcome variable is divided into distinct categories. On the other hand, if our y variable or the variable we want to predict is measured, in that case, it is called a regression task. So for example, the snow depth is being measured. So in this case, we are doing a regression task in our tutorial. So for the rest of this tutorial, we'll focus on supervised learning task with a special concentration on regression task. And again, we are focusing on regression task because we are predicting snow depth, which is a measured variable. So for us to be able to do machine learning, at least for this tutorial, we need to install two packages. We have the Tensorflow and we have the Keras. Tensorflow is an end-to-end open source platform for machine learning. It was developed at Google and it supports most of their large-scale machine learning applications. You can read more about Tensorflow if you click on this. So this is their website. You can read more about Tensorflow there. Then we also have Keras, which is a deep learning API written in Python, running on top of machine learning platform called Tensorflow. So Keras runs on top of Tensorflow. So the back end of Keras is really Tensorflow. And then we always want to use Keras because it makes machine learning very easy. It's easy to program. So, and other packages you need comes pre-installed if you're using the Anaconda version. And then if you're using Anaconda, if you want to install this Tensorflow and Keras because it doesn't come pre-installed in Python, then all you have to do is to go to your Anaconda prompt, and then you type this command, pip install Tensorflow, and then pip install Keras, and then it's going to install it for you. So after installation, you would be able to continue with this tutorial. That is if you want to do it on your local computer. But if you want to follow this tutorial, there is a way to install it down. So which means if you follow this tutorial, you'll be able to install it when you get down below. So for this tutorial, both TensorFlow and Keras are versions 2.5, but it doesn't mean these codes are not going to work on lower versions, but the ones that I use for this tutorial is version 2.5. So most machine learning techniques can be characterized as either parametric or non-parametric. We've talked about why we have to estimate F. Now, how do we estimate F? So to estimate F is divided into two. It is either parametric or non-parametric. A common parametric method is a linear regression, while a common non-parametric method is a neural networks. And then in this tutorial, we are going to focus more on two machine learning algorithms. The first one, which is a very simple algorithm, is the linear regression. And the other one we'll be using is neural networks. Both are machine learning algorithms. Linear regression, it assumes a linear form. It assumes that the relationship between your predictor variables and then the outcome you want to predict is linear. And in this case, when you have this kind of, when you assume this kind of relationship, the goal of machine learning is to estimate the parameters of the model. In this case, which are the beta naught, beta 1, beta 2, up to beta k. Beta naught is the intercept, while beta 1 up to beta k are called the slopes of the linear regression. So whenever you assume this kind of shape, then what you are doing is called linear regression. So linear regression is a parametric approach. And the reason why it is parametric is because it simplifies the problem of estimating your function down to just parameter estimation. But the disadvantage of using this kind of approach in the machine learning is because not all relationships are linear. As we see in the scalar plot above, you see that none of the relationship between the X and the Y variables are actually linear. So this is one of the major setbacks of using the parametric approach, because when you assume a functional form, by functional form, I mean shape. So when you assume a shape, it does not always match the true shape. But then one of the advantages, it is really fast. And then since all you have to do is to estimate parameters, it is really a good way to go if you want a fast algorithm. And one other major advantage of using this kind of parametric approaches is it is well suited for inference purpose. So if you want to look at how changing X affects your Y, then you are most likely to use a parametric approach. So now that we have mentioned the linear regression, the way in which the parameters of a linear regression are being estimated is using, we have two approaches basically. We have the gradient descent, and then we have the ordinary least square approach. So there is a little note on how to do that in the appendix, but then I won't talk much on it. But if you go down to appendix A here, you see there are two ways to do that. We have the ordinary least square approach, and then we have the gradient descent. And in this tutorial, the one we'll be focusing on is the gradient descent, which is just you initialize some weights and biases randomly, then you adjust the weights until you have the minimum or until you have the best results. So by best results, I'm going to explain what I mean by best results just in a second. So performance evaluation. Now that we have assumed a particular functional form for our model, we need to evaluate it. We need to know how well this model is performing. And that is why we have to evaluate its performance. So every time we estimate the true value using any trained machine learning algorithm, we have to measure the discrepancy, that is the error. We have to quantify this discrepancy, which is just what the difference between what we predict and what we observe. So there are many ways to quantify the error between what you predict and and the ground truth. So this is called loss function. Loss function is a function that quantifies the error we sustain from predicting Y with F. So in a simple language, it tells us how well our machine learning algorithm is doing. So loss function, we have different types of loss function, at least for regression case that we are working on in this tutorial. We have different types of loss function. And then the first one we are going to talk about is called the squared error loss. So one way to quantify the discrepancy between your predicted value and the outcome value and the true value is just by simply taking the difference between the two. But then one disadvantage of doing that is some of these discrepancies are going to be positive and some of these discrepancies are going to be negative. So when you add everything up, then they are likely to cancel out. Then every time you might always get 0, even though my machine is not doing well. So to overcome that, we always put a square. And in this case, this kind of loss function is called the squared error loss. That is, you square the error you get from predicting Y using f of x. So the reason for this square is to what? Is to avoid the errors canceling out, and then it is also for mathematical convenience. If this function is squared, then we'll be able to optimize it. Another way for which you can quantify our error is taking the absolute value of the difference between your outcome variable and your outcome value and the predicted outcome. So in this case, when you subtract the difference, you just take the absolute value. So with that, all your error is going to be positive, and then you can have a sense of how large your error is. This is often called the L1 loss. And then when you square it, it is often called the squared error loss. So it is worth noting here that this loss function as written here corresponds to one observation. So if we have 1,000 observations in my training set, so we have 1,000 of these values. So in practice, we want to quantify the loss over the entire data set. And then quantifying the loss over the entire data set is called the empirical risk, or some people call it the objective function. Some people call it the cost function. So, but whatever name you decide to call it, what we want to do in machine learning is to minimize the empirical risk, which is the risk quantified over the entire data set. And quantifying the risk over the entire data set is really just adding the losses for all the observation, and then you divide it by the sample size. So if you are using the squared error loss, then your empirical risk is simply the mean squared error. And then if you are using the mean absolute, if you are using the absolute difference between your y and the predicted y, then your loss function is called the mean absolute error. Your empirical risk is called the mean absolute error. And then you could find more losses here. So there are many losses you can use in regression. We have the mean squared error loss, mean absolute error. We have many of them here. So we can always choose anyone we want to use in minimizing. We can always choose the one we want to use. So now the next thing is we'd like to do some modeling setup. But before going to modeling, I would like to check Slack if there are questions. Quick help. Okay, I think I can continue for now. So modeling setup. So for this tutorial to run successfully, we have to install the Tensorflow. So, but in this case, you don't have to, if you're working directly on the Jupyter Lab, you don't have to use the Conda way that I mentioned above. You can just run this code and it's going to install it for you. So in this case, we're not using Conda, we are using the Mamba, and it's a Python package management also. It is an alternative to Conda and the pip that I mentioned above. So if you run this guy now, it's going to install this package. And then after installing it, we import the TensorFlow as TF. And then you couldn't import it as anything, but using TF is just the Pythonic style. This is what people often use. So you import TensorFlow as TF, and Keras is part of the standard TensorFlow library. So when you do tf.keras, you are already using Keras. And then if you want to check the versions of your TensorFlow, then you can always use this code to do that. So now we have to start by building our linear regression, since we've explained everything about linear regression. So it's about time we build our first machine learning model, which is the linear regression. So the machine learning algorithm uses the linear regression model as stated above to fit the feature to the outcome. So it will initialize different weights. It will going to initialize different weights depending on the seed we set. So the advantage of this seed now is to always have the same results every time we run the model. So since the weights are initialized, if you want to have, since the weights are initialized randomly, if you want to have a reproducible result, then it is always good to set your seed. So by setting the seed, it uses the same initial weight every time you run your model, and then with that, you always have a reproducible result. Then the next thing here is to specify your sequential model. And then what sequential really means here is that the output of your previous layer goes directly into the input of the other layer. That is what the sequential means here. And then you specify the layer of your regression, which means since you are predicting just one snow depth, then you have this. Activation is none, and then the input shape here is really the number of independent variables you have, and here it is what, 4 of them. So the reason why I've used it like this is I don't want to write 4 directly. That will be hard coding, because if my variable changes, then I would have to come here to manually input the number of features that I have. But with this, If my data changes, then this picks up the shape of the number of features I have directly. And then the next thing I do is to compile my model after specifying the shape of my model. Then the next thing I do is to compile my model. And here by compiling, we simply means you have to, this is where you specify the kind of loss you want to minimize, and then you specify the optimizer you want to use. By optimizer, optimizer is just a particular algorithm that makes it very easy for you, or that makes the learning fast. So for example, if you have a very large training data set, your optimization is going to be very slow. By optimization, I mean parameter estimation is going to be very slow. So one way to make that fast is really by using the optimizer. So we have different optimizers, and if you come here, you can always see different types of optimizers here that we can use. But in this tutorial, I'll be using the Adam optimizer, and then this is the learning rates. In practice, the function, the risk we are trying to minimize is always, you start by, since you initialize your weights randomly, you always start by a very high error, and then you try to minimize it until you get to a very, very low error. So how fast you move is called the learning rate. As an example, I could just have something here, I'd say learning rate. So in practice, this is what it looks like. So in practice, this is what it looks like. This is what the risk functional looks like, or the empirical risk that I want to minimize. This is what it looks like. And then we always start from somewhere here because the weights are initialized randomly. Then we try to move to the bottom here where the error is the minimum. So the steps, how large we move down this hill is called the learning rate. And this is what is specified here. So learning rate is not always constant. It is problem dependent. So you almost try different learning rate and see the one that works for your problem. So here I'm choosing 0.001 because it works for the problem at hand. So when you are running your own model on your own data set, you have to look at the learning rate that works best for your own model. And then the loss here means the loss I'm using is the mean squared error. You can change it to the mean absolute error or anything you want to use. So the mean absolute error is minimized to find the optimal parameters, and a discussion of the different optimization methods is provided in Appendix A. So the next thing is we can print our model, and then by printing the model, it simply tells you the number of parameters you have to estimate. Since we have 4 features here, that means we have 4 slopes that we want to estimate, and then we have 1 intercept. That is why we have 5 parameters here to estimate. So the next thing is we have to fit our model. So by fitting the model, here we find the regression parameters. Using the data in the training set is very important to just use the training set and not the test set. And epoch is when an entire batch of the training set has been used. As I mentioned earlier here, we often start from a higher error and then we try to move down to the lower error. So the number of times we do that, or the number of steps we take, is called the epoch. And here we have 100 epochs here. It doesn't mean this is the best. So this is also a parameter, a hyperparameter that is not constant. It's problem dependent. So for some problem, 20 epochs is okay, but here I'm using 100. So you use the one that works best for your model. And here I also have the validation split. So the validation split here is 0.2, which means I'm using 20%. I'm using 20% of my training set as validation. So what the validation set does is it monitors my training. And when I plot the performance on the training versus the validation, and it's easy for me to see if my model is overfitting or not. By overfitting, I mean if it is performing well on the training set, but not performing well on the test set. So this is a good way to have a feel of what that means. And by this, verbose is 0. It means I don't want to see the per epoch output. If you want to see the per epoch output, then you can just simply change this one to 1, then you see the per epoch output. So after training my model now, it is good to always see if my model has converged. By convergence, I mean if the error is just constant with the epoch. So at 100 epochs, here we see, I think from around 80 down to 100, the error is fairly constant, which means what my model has converged. And that is the essence of this. And then when you also plot this, if there is a very large difference between the training loss and the validation loss, then you know your model is probably not doing well. So in practice, we want to have a model for which the training and the validation loss are not far from each other. So the next thing is, since we have a functional form, then we'll be able to write out my model. And then to get your model, to get your parameters from the trained linear regression, you just use this function get weights, and then it gives you this. And then you can fit your model, where 0.24 is gotten from here, which is simply my bias term or the intercept. And each of these values are the slope corresponding to each of the variables that I have. So this is the first, so this is the first model. And then the second model is going to be neural networks. So neural networks are a type of non-parametric method. And another non-parametric method is supervised support vector machines. We have boosted trees and the likes. So, but here we're not going to talk about them. We're just going to limit our discussion to neural networks. So, and non-parametric approaches do not specify any shape for F. So for the parametric approach, we specified that F is a linear function of the axis. But here we are not specifying any functional form. Instead, we try to estimate F that gets close to the data points as possible. So, and here the data points means the training data sets. Neural networks are machines that are inspired by the functionality of biological neurons, and they are not models of the brain, but then some of the concepts in deep learning or in neural networks were inspired by understanding the brain. So every neural network consists of 3 layers. We have the input layer, we have the hidden layers, and then we have the output layer. So to understand the functioning of these layers, we begin by exploring the building blocks of neural networks. So the building blocks of every neural network is a single neuron or a perceptron. So this is often how we represent a neural network, and each of these nodes here is called a perceptron. So each layer in the neural network consists of a small individual unit called the neurons, and then it is often represented by circles. A neuron receives input from other neurons. So just like this is a neuron and it receives input from these neurons here, and then produces an output. So it produces something here, and it also passes it to the next one here. Each neuron in the input layer represents the feature. So in essence, the number of neurons you are going to have in the input layer is going to be the number of features you have. So for example, in this problem we are trying to solve, or in this tutorial, we'll have 4 nodes in the input layer. And then each neuron in the input layer is connected to every neuron in the hidden layer. So as an example, this is connected to this, is also connected to this. This is connected to this, and this is also connected to this. And the number of neurons in the hidden layer is not fixed. So the number of neurons you have in the hidden layer is not fixed. It is problem dependent, and it is often determined via cross-validation. So you don't have a fixed number of neurons in the hidden layer. It is problem dependent. So it depends on your own problem. So here, the configuration of the hidden layer controls the complexity of your neural network. So when you have many nodes in your hidden layer, then you are beginning to have a very complex model. A neural network may contain more than one hidden layer. So which means you don't always have one hidden layer. A neural network with more than one hidden layer is called a deep neural network, while the one with just a single hidden layer is called a shallow neural network. So when you have more than one hidden layer here, then you are in the presence of a deep neural network. But if it is just one, we often call it a shallow neural network. The final layer of the neural network is called the output layer, and it holds the predicted outcomes of the observations passed through the input layer. So when you pass some observations here, it does some mathematical operation here, and then it brings the output. This output, where it brings the output, is called the output layer. Every interneuron connection has an associated weight. So for each of these connections, there are weights, and they are often initialized randomly. So when connections between the layers do not form a loop, so as you can see here, this is moving like this and like this. None of them is turning back. So in this case, when there is no loop, it is called feed-forward neural networks. And if there is a loop, it is called recurrent neural networks. In this tutorial, we'll concentrate on the feed-forward neural networks. So now it is at this point in time, we are going to introduce how the perceptron works. That is, each node in the hidden layer, what does it do? So each node in the hidden layer simply does a linear regression. So by this is just W0. Then if you expand this is just W1x1 plus W2x2, just like we have in the linear regression. But what differentiates this from a linear regression is this function G. And this function G is called the activation function. And what it does is it introduces non-linearity into the network. So if we didn't activate our network, what we are simply learning is a linear function. But by adding activations, what we are doing is introducing non-linearity into our network. And then we have different activation functions in practice. We have the sigmoid, we have the hyperbolic tangent, we have the rectified linear unit. The most common one, the commonly used one, is the rectified linear unit, but also it is problem dependent, it is not fixed. So you use the activation function that works best for your model. So this is just a chunk of code that shows us the shape of the activation function. This is what a segment activation function looks like, and what it does is any value you pass into it, it squashes it between 0 and 1. Then for the hyperbolic tangent, any number you pass through it, it squashes it between -1 and +1. And then for the rectified linear unit, it just picks the maximum between 0 and the particular number. So if what you are bringing is negative, then it returns 0. But if it is positive, it returns the particular value. So now that we've known the activation function, it is a good time to introduce the families of neural networks. There are different neural networks in practice. And then we have the feed-forward neural networks, which is the one I introduced in this tutorial. And it is often used when we have a structured data set. By structured data set, I mean when your data is in table format. We have the convolutional neural networks, which is often used for image classification. Then we have the transfer learning, which simply means you use the knowledge from a previous task on a new task. So as an example, if you have built a neural network that recognizes the face, then you want to build a neural network that recognizes the hair. So since you have a neural network that recognizes the face, then you don't have to start from scratch. You just use that neural network as the starting point for the one that recognizes the hair. So in that case, what you are doing is called transfer learning. So we also have the recurrent neural networks, which is well suited for text analysis or time series, or when you want to do some drawing generation. We have the encoder, decoder, which is commonly used for machine translations in cases that you pass in English and then it gives you the translation in other languages. We have the GAN models, which is always used for 3D modeling. And then you have the graph neural networks, which is commonly used to work with graph data sets. So in this tutorial, we are focusing on feed-forward neural networks. And then here we go. The first step is we specify the architecture of the model. By specifying the architecture, I mean you have to specify the number of hidden layers you want, and then the number of nodes in each hidden layer. So for this tutorial, I'm using 3 hidden layers with 1000, 512, and 256. And again, it is important to note that this is not constant. It depends on the problem at hand. So again, for reproducible results, I'm setting my seed to 1000 here. And then I define my model sequential as what? As network. So just as I have before, this first line of code, what it does, it specifies the input shape. Here I have 4 inputs, And just like I did it before, I didn't write out the for because that will be hard coding. It just picks up the shape based on the training X that I have. And I'm specifying the activation function as ReLU. And I'm saying the number of units is 1000 nodes in the first hidden layer. Then the second hidden layer, I have 512. I also have ReLU activation. And then the third hidden layer, I have 256 nodes, and I have the sigmoid activation. And again, you could change these numbers. They are problem dependent. You could change this also. They are problem dependent. And then I have my final layer, which is the output layer. And here, since I have just one output that I'm predicting, which is the snow depth, then the number of units in my output is just one. So everything here is not constant, but here it depends on what you are doing. If you are predicting a continuous variable, definitely you have one. But if you are predicting a categorical variable, then the number of categories you have is going to be the number of units you have in this last layer. And then the number of layers I have 3 in this case, it is not constant. So it could be 2, it could be 1, it is problem dependent. So the next thing is you compile. And just as we said before, when you compile, what you do is you specify the loss function and then the optimizer you want to use. Optimizers are just what you use to make your learning process fast. Then the next thing is we have to print our architecture. And then it means here for this architecture that I specified here, I have 649,094 parameters to estimate. And then how are these calculated? So we start by what? The first hidden layer here has 1,000 inputs, and then we have 4 features from the input layer. So when you multiply 1,000 by 4, you have 4,000. And for each of the nodes in the first hidden layer, they are accompanied by what? By biases. So we have 1,000 of them. So when you add it up, you have 5,000. That is how this was gotten. Then also for the second one, for the second hidden layer, it has 512 nodes. And then when you multiply this 512 from what you have from the first hidden layer, which is 1,000, and you have the 512 biases, then you have these particular values, then same applies to the third hidden layer, and same applies to the final outputs. And that is the computation of all these are done here, just following the same approach here. So the next thing is we fit our model. Here I've used 20 epochs, and also it is not constant, it is problem dependent. If your model has converged after 20 epochs, then it is fine. If it does not converge, then you increase the number of epochs. If you want to see the epoch, if you want to see the per epoch training, then you can change these variables to 1. So also, after training your model, it is a good idea to plot your training loss and the validation loss. So here we expect that the training loss and the validation loss should not be far from each other. So if they are far from each other, that is, if there is a wide gap between your training and the validation loss, then you can have some sense, in some sense, you can know that you are overfitting your training set. And by overfitting, it means the model is going to perform well on the training set and it's going to perform poorly on the test set. So that is why we do the validation split. So one way to know if your model is overfitting is you would see at some point the training loss and the test and the validation loss will begin to diverge. That is, the training loss is going to be getting smaller while the validation loss is going to be getting bigger. So at that point, you know you are overfitting your training sets. And then one common practice is to stop your training when you see that overfitting has started. So after training our models, the next thing is we want to predict. So we have used machine learning to build 2 models now. So we have built 2 machine learning models. The first one is the neural network and the second one is the linear regression. So now we would use the computer models or the machine learning models to estimate snow depth for a given set of features, which is the phase, coherence, amplitude, and incidence angle. So that is what we are doing here. The first one is for the linear regression, and then I use linear regression.predict and predicting my test sets. So, but then it is important to note that we have normalized our variables. So by predicting here, we are predicting the normalized version of our snow depth. But in practice, we are not interested in the normalized version of our snow depth. We are interested in the true value of our snow depth. So by that, we have to get the inverse transformation, and that is what I'm doing here by just getting the inverse transformation of my predicted value. So with that, I'll be able to compare it with my true value. I did the same thing for the deep neural network. And then this is my true value. And I'm putting everything together into a data frame. So the next thing is to check my performance. If I want to check my performance on the test set, there are many ways to do that. So but in this tutorial, I'm going to use the root mean squared error, the R square, which is often called the coefficient of determination, and the MAPE, which is the mean absolute percentage error. So the root mean square is going to be in the same units with my y variable. So if the root mean square is 0, that means my prediction is perfect. And if it is large, the larger the root mean square, then the larger the error. So we'd always want a root mean square closer to 0. Also, my R square takes value between 0 and 1. And when my model is really, really bad, it could have a negative value. So the closer to 1, the better the model. So when my R square is a perfect 1, it means my observed and my predicted values are the same. That is, my model has predicted my observed values perfectly. Then MAPE is just like putting the error into percentage. So by doing that, I have my linear regression results and I have my deep learning results. So comparing the two, so even at 20 epochs, and this is 100 epochs, even at 20 epochs, my deep neural networks has really outperformed these. And then we could connect this difference in performance to the shape we observed in our scatter plots. We saw that the predictors or the features are not linearly related to the outcome variable. So we expect to have a very poor performance we expect to have a poor performance from the linear regression. And then the next thing we could do is we could visualize our performance using some scatter plots. So this is one way to know how well your model is doing. So this is supposed to be a perfect straight line if my predicted value and the true values are the same thing. So here we see more spread. The more spread out it is, then the bad the model. So since this is more spread and this is less spread compared to this, then you see that this is doing well. But in practice, if you have a perfect model, then this is just going to be a straight line. So one other thing we could do is to visualize our uncertainty. And there are many reasons why we have to do this depending on the discipline that you are. But if you want to visualize your uncertainty, then one way to do it is using the histogram. And you see the error for the linear regression is between -1 and 1.5. Then for the deep neural network is between -1 and 0.5. So we see more spread here than here. And then the closer the errors to 0, then you have a histogram that is not spread out, which is closer to the center here. So one thing we can also do is after getting the preferred model, we could always save the best model so that you don't always train your model every time. So Keras gives us an avenue to do that by just picking the name of the model and have .save. So here I'm saving it as DNN. So when you run this line of code, it saves this model as a particular folder. So by saving the model, it keeps all the weights, all the activations, every architecture you've used is saved, and then you don't have to retrain your model again. You just have to use it for prediction anytime you want to use it. So, and to load a saved model in Keras, you just use the function load model, and then you put the name of the model. So here I'm saving it as DNN, then I'm loading it again as DNN. So now I saved it into model, then I could just use model.predict to predict my new observations. So there are some challenges in machine learning. Basically, we have it is categorized into two. we have bad data and bad algorithm. So by bad data, we mean you could have insufficient training data sets. So as an example, in this case, we only have 3,000 training observations. So if we had more observations, then it is expected that the deep neural network is going to learn better with more observations. And then non-representative training data sets. So if the kind of training data set you have is very different from the kind of data set you would expect in your test data set, then you expect your model to perform very poorly. So, and that could be as a result of your selection bias while getting the data sets. So when you are getting your data set, it's important to always avoid bias. So you try to, and that is why we also did a random selection for our training sets. So if your training set is not representing your test sets, then you expect your model to perform poorly. Then irrelevant features, if you have some features in your model that are not relevant, then it could also cause poor performance. And in practice, there are ways by which you can select the relevant features from your model. So the other one is bad algorithm. You could have a bad algorithm. By that, it's overfitting the training data set. So by overfitting the training data set, what I mean by that is your model is typically going to perform well on the training sets, but it's going to perform really poorly on the test set. So in that case, we call it overfitting. So by underfitting, it means the model is not performing well on both the training and the test set. And common causes of overfitting is when you have a very complex model. So the more complex the model, then the higher chances of overfitting the training data set. And then we have an extremely simple model, then you are likely to underfit your training set. So there are various ways to improve your deep learning models. The one I just built is a very simple one. You could always improve that by regularizing. And by regularization, I mean, you could have early stopping, you could have dropout, you could have L1, L2, and the likes. So by early stopping, what I meant is you're going to come here and try to monitor this per epoch. I'm going to monitor this. So you notice the epoch for which the difference between the training loss and the validation loss becomes bigger. So at that place, at that epoch, then you stop training. So that is what we mean by early stopping. And then by dropout, it means you are just going to randomly set some weights to 0 when you are training that for a particular epoch. You just randomly set some weights to 0. So by that, it reduces the complexity of your model. And then if your model is less complex, then there's less chances for it. There's a less chance for it to overfit your training sets. And another way to improve your deep learning model is hyperparameter optimization. So by hyperparameter optimization, so I start by defining what an hyperparameter is. Hyperparameter is or are parameters that are not learned when you are training your model. They are specified before training your model, and then they control the performance of your model. So for example, in deep learning model, there are things you have to specify before training your model, such as the number of hidden layers you would have, such as the number of nodes you are going to have in each of the hidden layers, such as the optimizer you are going to use, such as the learning rate, such as the activation functions. You could change all those things. So that is what we mean by hyperparameter optimization. So one way to do that is you just keep changing the values. Maybe since I use 3 hidden layer now, you could change yours to 2 and compare the results. Then since I used 1000 in the first hidden layer, then you could change, maybe you change it to 500 and see how it performs. Maybe you change the activation function in the first hidden layer from ReLU to sigmoid, you change the learning rate, and you just try to randomly select those things to see the outcome, then you pick the best model. Then another way is to have a grid search, and that is going to require a high computational, that is computationally expensive, because you are going to specify different values of the hidden layer, different number of hidden layers, different number of neurons in the hidden layers, then different number of learning rates, different number of different activations and the likes. So then you do like a cross-validation on it, but that is, it's going to start pairing each of those for all possible combination it could have. So then in the end, you have results for everything, and you pick the one with the best performance. So that is one way to also go about the hyperparameter optimizations. There are ways to do that in Python, but then if you have a very large data set, then you should expect that it is going to take a long time for it to run. It could take hours, it could take days at times. So depending on how large your data set is and how large the hyperparameters you specified are. So by large hyperparameters, I mean maybe you specified 10 hidden layers for it to 10 combination of hidden layers, 10 combination of each node of the hidden layers, then so by that it has to do all the combinations, and for it to run, then it could take a long time for it to finish running. And before going to this, I'd like to acknowledge HP Marshall, who gave me the opportunity to be a part of this Hackweek, and then a huge thanks to the University of Washington team and Scott. I disturbed him a lot for him to help me upload my tutorial on the Hackweek website. So thank you very much, and thank you to everyone here also. And these are some references that you could go to. These are links that you can click and learn more from. And these are the appendix. If you want to learn more about the optimization of the linear regression, you have the ways that which you could optimize the ordinary least square, the gradient descent. And if you want to learn more about neural network optimization, I kept a little note about that here. So before trying this out, I'd like to see if there are some questions in Slack for me to answer.